about analyticity of harmonic functions. So in the previous lectures, we have established that harmonic functions infinitely differentiable, differentiable infinitely many times, right? They see infinity. And indeed, we had this representation for any C2 function in domain omega, in the closure of omega. For harmonic functions, we have the following representation. And from this representation, we can see that if point x naught is in omega, and integration is over the boundary, so x is on the boundary, then we can differentiate this function under the integral with respect to x naught any number of times. Phi here is the fundamental solutions that we discussed in many lectures, so we know the explicit formula for phi, so we know that we can differentiate this function with respect to x naught infinitely many times. Because when x naught again is in omega, so it's not equal to x. And okay, so next step would be, if we think about expanding our function into a Taylor series. So to have a Taylor series representation, we need to compute the coefficients. Coefficients depend on derivatives. So if we know that our function can be differentiated infinitely many times, then we will be able to compute all of the coefficients. We will be able to compute all of the derivatives. Does it mean that our function can be just, not our function, just in general, that such a function, C infinity function, can be expanded into a Taylor series or power series, we can say? The answer is no, because in addition, we need the convergence of the series, right? We need the convergence. And there is a famous example when we have a function that is differentiable infinitely many times, but there is no convergence of Taylor series. And here is this example, f of x equal e to the negative 1 over x squared when x not equal to 0, and 0 when x equals to 0. And here, this example is about function of one variable, single variable x. And if we try to write Taylor polynomial centered at 0, we will get it. We will get an identically zero polynomials. And if we compute our function at any point x, when x is not 0, in a small neighborhood of 0, we will get a positive number. So there is no hope to have our Taylor series converging to the value of our function at point x. So this was just an example to explain the difference between infinitely differentiable functions and functions for which Taylor series makes sense. But it turns out for harmonic functions, we will have, we have already convergence of Taylor series. And such functions are called real analytic. So here I wrote the definition. So let function f be a function defined on an open set omega in Rn, whose range lies in R. We call f of x real analytic at point x sub 0 in omega if there exists a neighborhood of point x naught such that for any x in this neighborhood we can write down Taylor series. So C alpha, here are some coefficients, or let's say for now power series, right? So C alpha some coefficients, and then we say that f is real analytic in omega if f is real analytic at each point, right? So if the series converges at every neighborhood at neighborhoods of every point in omega, right? So here in this definition we are talking about functions of several variables, and I want to show that for harmonic functions our power series is Taylor series, and this series converges. But before proving this main theorem, I just want to remind you how to write down Taylor series formulae. And this formula you perhaps remember, this is just a Taylor series written for a function of one variable. So here x is one independent variable, so and we can write down Taylor series at centered at point A, right? So that would be f at A, f prime at A, x minus A plus second derivative evaluated at point A over 2 factorial x minus A squared, and so on. If I want to generalize it to the case of several variables, the simplest way to be rewrite this formula in terms of differentials. So let's look at this term, right? First term, x minus A we can call delta x, or we can call dx, right? X independent variable here. And then the whole thing will be our first differential. So I wrote it here that f prime of A, x minus A, is our first differential. Then differential of differential is second differential, and in the case of independent variables, a variable it will look like second derivative at point evaluated at point A, right? What we have, and dx. So this term can be written as second differential divided by 2, and then the third term can be written as the third differential divided by 3 factorial, and so on. So I wrote it here, right? So I wrote f of x equals f of A plus the f evaluated at point A, because we evaluate derivatives at point A, plus 1 over 2 factorial second differential at point A, and so we can rewrite everything if I mean on the differential of 0 order, just function itself. So I can write a sum k from 0 to infinity 1 over k factorial k differential of f at point x equal a. Right? So far this is familiar from calculus. What some of you haven't seen in calculus for some reason is this formula. So if now we have a function g that depends on n variables, or we call it g of x, where straight x this is just our vector, then we can write this formula in the same way using differential as a sum of dk at point g or k factorial on x evaluated at point x naught, and have this formula for have this Taylor expansion for our function of n variables. So here I again wrote that zeroth differential, what I mean under zeroth differential, I mean just function itself. What is first differential? It will be just say if we apply it to a function, right? Then it will be first derivative times dx1 plus first derivative with respect to x2 times dx2, and so on. So if I write it as an operator, right, just d d dx1, d dx1, plus so on, then it's easy for me to write kth differential. Again, here we assume that we have n independent variables, and then kth differential, we just can formally take this expression and raise it to power k. In addition to Taylor series in calculus, we've been talking also about Taylor's formula. It's when we write first few terms and then we write the remainder, right? There are different forms of remainders, and I wrote here, and we'll be using today remainder in the Lagrange form. So it's when we say compute first differential at point x0, and the last term we write as n plus first differentials at some point in the neighborhood of point x0 where we have our expansion. And now let's do an example just to illustrate how we can write as a few first terms. So consider this function g of x1, x2, which is e to the x1 cosine x2, and let's write down a few terms of the expansion centered at point 0, 0. So first term, we just write our function and evaluate it at point x0, which in our case is 0, 0, so it will be e to the 0 cosine to the 0, that would be just 1. And then we compute the first differential. So I wrote here all of the details. So we take our function, we differentiate it with respect to x1, then we plug our point 0, 0 times dx1, then plus differentiate our function with respect to x2 and plug the point times dx2. So here I computed derivative. When we differentiate this one with respect to x1, it still will be e to the x1 cosine x2 dx1. I intentionally didn't plug the point yet because I want to differentiate it again. Then second derivative will give us, we differentiate cosine, we get negative sign, and if we now plug point 0, 0, here we will get 1, and here sine of 0, 0 will get 0. So the whole thing would be dx1. And then we differentiate it again. So here I didn't use the general formula, I didn't use this formula, since I already computed first differential. Now I differentiate it again. So I take this term, differentiate it with respect to x1. I'm getting e to the x1 cosine x2. So, and then it will be times dx1, so dx1 squared. Then I take this term and differentiate it with respect to x2. When I differentiate it with respect to x2, I will get, instead of cosine x2, I will get negative cosine, negative sine x2. And then it will be times dx2. So here we have, and I will get similar term from here when I differentiate this term with respect to x1. So that's why I have two terms of like this. And then I take the last term, and I already differentiated it with respect to x1. So now I differentiate with respect to x2. So sine will become cosine and dx2 squared. And then I plug point 0, 0. So from here I have this coefficient as 1. This coefficient would be 0 because sine of 0 is 0. And here again I have coefficient of 1. So I have dx1 squared minus dx2 squared. And then to write down the final expression, so it's not final, we can continue. Of course, I just wanted to illustrate how to compute first two terms. So then this one then we replace with the term x1 minus our x1 0. In our case, x1 0 is 0. Since this is 0, so then it will be just x1. And similarly here, then we will get x1 squared, and from here x2 squared. So finally we have 1 from here, then we have x1 from here, and then we have 1 over 2 factorial x1 squared minus 1 over 2 factorial x2 squared, and then we can continue. The next term will be 1 over 3 factorials, and then it will be this third differential, and so on. So to show that harmonic functions are real analytic, we need to prove the convergence of the Taylor series. And our first step in this direction would be to find estimates for derivatives of harmonic functions. So here is our first theorem. So let u of x be harmonic in omega and continuous in the closure of omega, and let omega 1 be domain inside omega, so subdomain, and let rho be a distance between omega 1 and the boundary of domain omega. Then for any x in omega 1 and for any, I put here, I will use here multi-index notations, alpha equals k, we have the following estimate. And here, so alpha would be multi-index, so the notation is, I will use capital D with subindex xj for derivative with respect to xj, and then I can use d alpha when I just have a derivative with respect to each variable so many times. And this notation means that we just the order of derivative. And rho here, distance, is the infimum of x and x naught, that is greatest lower bound, and we assume here that x belongs to the domain omega 1 and x tilde, I said x naught, x tilde belongs to the boundary. And k here is a positive integer. Right, so a lot of notations, but so here is our main goal, and we will prove this theorem in 3 steps. So first step, we claim that this derivative, the alpha u, is harmonic in omega. And indeed, we just discussed that our function u is c infinity in domain omega. So if we want to compute Laplacian, right, to show that it's harmonic, to compute Laplacian, we just apply Laplacian to d alpha u, and we can change the order, so it will be d alpha of the Laplacian. So this is 0, so the whole thing is 0. Right? First step was pretty easy, straightforward, that d alpha u is harmonic. So in the second step, we will just talk about a ball. Right? It's not the domain omega itself, but about a ball. So we have, we claim that we can have this estimate in a ball centered at some point x naught of radius r, when the entire ball belongs to our domain omega. Then absolute value of derivative with respect to xj at a point x naught less or equal than nr radius of our ball, and here we have maximum of absolute value of our function u in the closure of the ball centered at point x0 of radius r. And j here is the just indicates the variable. And so indeed, let's see that we know that dxju is harmonic in the ball, and this function is continuous in the closure of the ball, at least. So then we can apply mean value theorem that we discussed in lecture 19, and it will be, we will write a version for a ball. So mean value theorem for a ball. So then we can say that value of this harmonic function can be written as the average, so across over the ball, and this is our volume of our ball, right? So cap n is volume of a unit ball of this function. And so we have this mean value property for a ball, and then we apply to this formula, we apply formula that we discussed in lecture 17, that we can switch from integration of the area to the integration of the boundary. And here it will be jth component of our outward unit vector. So if we specify this formula for function dx derivative of with respect to xj of our function u at point x0. So if we look at this integral, so we will copy this term, and then instead of integral over the ball, we will have integral over the sphere, and then instead of derivative using this formula, we just write u nu j. And then we will just evaluate left hand side would be less or equal than if we put absolute value under the integral, and then it means that we can write that it will be less or equal than maximum of absolute value of u over the closure of our ball times area of surface area of our sphere, which is omega n r n to the -1. And then here we use the formula that we derived in lecture 19, how kappa n, so volume of the unit ball and surface area of the unit ball are related. We use this formula, we replace kappa n with this term, and then omega n will be cancelled, and r to the n-1 will be cancelled, and then we will have n over r times maximum of absolute value of u over the closure of the ball. That is the formula that we wanted to get in our step 2. So to finish the proof, we will make our third step, and we will consider domains omega 1, omega 2, omega k plus 1, such that omega j belongs to omega j plus 1, and j here runs from 1 to k. And omega k plus 1 coincides with our original domain omega that was given in the statement of the theorem. And also we have another condition that distance between omega j and the boundary of omega j plus 1 is rho over k. And then, so here I just drew omega j plus 1, and then we can consider any point x naught in omega j. And if we look at the ball that is centered at x naught and has radius rho over k, then the entire ball would be in the domain omega j plus 1 because of this condition, right, the distance. And then we can write the following inequality. If we look at, but to write the following inequality, this inequality, we will just recall that from step 2, for a ball, we had this estimate. And then we can write that in the closure of omega j, our derivative of order alpha can be estimated as n k over rho, because here we have radius, now radius is would be, can be written as k over rho, and also sorry, rho over k, but 1 over radius k over rho, and then it can be estimated through the maximum of the derivative of order alpha prime of our function u in the domain, in the closure of domain omega j plus 1, when the order of alpha is k minus j plus 1 and alpha prime k minus j. So derivative d alpha u is d derivative with respect to some variable xl of d alpha prime of u, where l is just a number between 1 and n, right? Number of our derivative, not the number, just our l derivative with respect to our l variable. And then we can write that maximum of d alpha u in the closure of domain omega j. So here it was through the another derivative of lower order. And then if we want to rewrite everything in terms of maximum of modulus absolute value of function u in the entire domain, then we can write these estimates, and from here the inequality that we wanted to prove just immediately follows. So this finishes the proof.